So, here's something to think about as you settle in tonight. Right now, wherever you are, you're wrapped in a blanket of air that stretches about 100 kilometers above your head. And that air, that thin, invisible shell around the planet, is doing something so quietly extraordinary that for most of human history, nobody even thought to ask how it worked. It's keeping you warm. Not warm like a blanket keeps you warm by trapping heat close to your body. Although, that's actually not a terrible analogy. It's keeping the entire planet warm enough for liquid water, for rain, for rivers, for life. Without that atmosphere doing its thing, the average temperature of Earth's surface would be something like minus 18 degrees Celsius. That's below 0 Fahrenheit. The oceans would freeze, and yet here we are at a comfortable global average of about 14 or 15 degrees Celsius, give or take. That difference, those 33 degrees of warming that the atmosphere provides just by existing and having the composition it does, that's the story we're going to wander through tonight. How people figured that out, how long it took, how many wrong turns and brilliant guesses and stubborn arguments it involved. And honestly, it's one of the most fascinating stories in all of science, because it touches everything: physics, chemistry, geology, biology, mathematics, politics, even philosophy. And it starts, like so many good stories do, with someone simply looking up and wondering. The ancient Greeks, as they tended to do, got there first, or at least they started asking the right kinds of questions first. Around 350 BC, Aristotle wrote a treatise called Meteorologica, and that title is where we get our word meteorology. Now, Aristotle wasn't doing climate science in any way we'd recognize. He didn't have thermometers, he didn't have barometers, he certainly didn't have satellites. But he was doing something crucial. He was trying to systematically describe the atmosphere as a physical system. He talked about evaporation, about how water rises from the sea and falls again as rain. He described wind patterns. He even divided the Earth into climate zones: the torrid zone near the equator, the frigid zones near the poles, and the temperate zones in between. And that word, climate, comes from the Greek klima, which referred to the inclination of the sun's rays at different latitudes. So from the very beginning, people understood that climate had something to do with how sunlight hits the Earth at different angles. That's a pretty solid starting intuition, actually. But here's the thing. For nearly 2,000 years after Aristotle, progress on understanding the atmosphere was, well, glacially slow. And I use that word deliberately, because glaciers are going to become very important to this story later on. The problem was that you can't really do atmospheric science without instruments. You need to measure things: temperature, pressure, humidity. And those tools simply didn't exist for most of human history. You had brilliant minds. Islamic scholars during the medieval period made significant advances in optics and mathematics that would eventually feed into atmospheric science. But the raw observational tools weren't there yet. That starts to change in the 1600s, and it changes fast. Galileo, or possibly one of his students, the historical record is a little fuzzy on this, develops an early thermometer around 1603. It's crude, it's not very accurate, but it's a start. Then in 1643, Evangelista Torricelli, who had actually been Galileo's assistant in the last months of the old man's life, invents the mercury barometer. And this is a big deal. Torricelli fills a glass tube with mercury, inverts it into a dish of mercury, and watches the column drop to a certain height and stop. He realizes that the weight of the atmosphere pressing down on the mercury in the dish is what's holding that column up. He's literally weighing the air. And he makes this beautiful statement. He says we live at the bottom of an ocean of air. Think about that image for a second. You're lying there right now at the bottom of an ocean. It's just an ocean made of gas instead of water, and it has weight, and it presses down on everything, and it behaves according to physical laws that can be measured and understood. Now, once you can measure temperature and pressure, things start to accelerate. But the real story of climate science, the part where people start to understand how the atmosphere actually regulates Earth's temperature, that doesn't really begin until the early 1800s. And it begins with a man whose name you might not know, but whose work quietly changed everything. His name was Joseph Fourier. You probably know Fourier, if you know him at all, from mathematics. Fourier transforms, Fourier series. If you've ever taken an engineering or physics course, his name was probably on the board at some point. He was a French mathematician and physicist, born in 1768 in Auxerre, a town in Burgundy. His life story is remarkable all on its own. He was orphaned by age 9. He was educated by Benedictine monks, showed extraordinary mathematical talent, got swept up in the French Revolution. He was actually arrested during the Terror and came close to the guillotine. Then, Napoleon took him to Egypt as part of the scientific expedition that accompanied the military campaign, and Fourier spent years studying Egyptian antiquities and, crucially, experiencing a very different climate than the one he'd grown up in. Some historians think that time in Egypt, feeling that intense desert heat, might have planted the seed of his later interest in how heat moves through materials and through the atmosphere. When Fourier returned to France, he threw himself into the study of heat conduction. His masterwork, The Analytical Theory of Heat, published in 1822, is one of the great works of mathematical physics. But tucked inside his broader work on heat, Fourier asked a question that nobody had really asked before in a rigorous scientific way. He asked, why is the Earth as warm as it is? See, Fourier understood something that seems obvious once you hear it, but that nobody had really worked through carefully. The Earth receives energy from the sun. It absorbs some of that energy and warms up. But a warm object radiates energy back out into space. That's just basic physics, even by the standards of the early 1800s. So there should be a balance. Energy in, energy out. And when Fourier did the calculations, rough calculations, mind you, but calculations, he found that the Earth should be considerably colder than it actually is if the only thing going on was sunlight coming in and heat radiating back out. Something was trapping some of that outgoing heat. Something in the atmosphere was acting as a kind of insulating layer. Fourier used an analogy that's both famous and slightly misleading. He compared the atmosphere to the glass of a greenhouse, or more precisely, to a device called a heliothermometer that a Swiss scientist named Horace Benedict de Saussure had built decades earlier. De Saussure had constructed these insulated boxes with glass lids, nested inside each other, and showed that the interior got much hotter than the air outside when placed in sunlight. The glass let sunlight in, but trapped the warm air inside. Fourier suggested the atmosphere did something similar. It was transparent to incoming sunlight, but somehow impeded the escape of heat radiated from the Earth's surface. Now, this is where the term greenhouse effect comes from, and it's worth pausing for a second to note that the analogy isn't quite right. A real greenhouse works primarily by preventing convection. It stops warm air from rising and blowing away. The atmosphere's warming effect works differently, through the absorption and re-emission of infrared radiation by certain gases. But the name stuck. And honestly, As a rough, intuitive picture, it's not terrible. The key insight, that the atmosphere lets sunlight through but partially blocks outgoing heat. That's exactly right. And Fourier got there first, in the 1820s. But Fourier couldn't identify the mechanism. He knew something in the atmosphere was trapping heat, but he didn't know what. He didn't know which components of the air were responsible. And this is where the story gets really good, because the person who figured that out was one of the most unlikely scientists in the history of the field. Her name was Eunice Newton Foote. Foote was an American scientist and women's rights activist. She was at the Seneca Falls Convention in 1848. In 1856, she conducted a beautifully simple experiment. She took glass cylinders, filled them with different gases, put thermometers inside, and set them in the sun. She tested regular air, moist air, and carbon dioxide, which at the time was called carbonic acid gas, and what she found was striking. The cylinder filled with carbon dioxide got significantly hotter than the others, and it took much longer to cool down once removed from the sunlight. Foote wrote, and I'm paraphrasing only slightly, that an atmosphere of carbonic acid gas would give the Earth a high temperature. She even speculated that this might explain why the Earth had been warmer in earlier geological periods. This is remarkable. In 1856, an American woman is publishing a paper that essentially identifies carbon dioxide as a greenhouse gas and connects it to past climate change. And yet, for over a century, she was almost completely forgotten. Her paper was presented at the American Association for the Advancement of Science meeting, but it was read aloud by a male colleague, Joseph Henry, rather than by Foote herself. And when the history of climate science was written and rewritten over the following decades, her contribution was overlooked in favor of a man who published similar but more detailed findings 3 years later. That man was John Tyndall, an Irish physicist working at the Royal Institution in London. And I don't want to diminish Tyndall's contribution. It was extraordinary, and in many ways more rigorous and complete than Foote's. But the fact that Foote got there first, independently, with simpler equipment, and was then essentially erased from the record for over 150 years, that's a story worth knowing. Tyndall, in 1859, built an elaborate experimental apparatus to measure the absorption of infrared radiation, heat radiation, by different gases, and his results were dramatic. He found that the main components of the atmosphere, nitrogen and oxygen, which together make up about 99% of the air, were essentially transparent to infrared radiation. They didn't absorb it at all. But water vapor, carbon dioxide, and methane absorbed it strongly. These trace gases, these minor components that make up less than 1% of the atmosphere, were doing all the work of trapping heat. Tyndall immediately grasped the implications. He wrote that removing water vapor and carbon dioxide from the atmosphere would essentially strip the Earth of its thermal blanket. He understood that these gases were the mechanism behind Fourier's greenhouse effect. And he recognized something else that's really important. He noted that water vapor was actually the strongest absorber, even stronger than carbon dioxide. This is still true, and it's a detail that matters enormously for understanding how the climate system works, because water vapor acts as a powerful amplifier of warming caused by other factors. But we'll come back to that. What I love about this period, the mid-1800s, is how the pieces are coming together from completely different directions. You have physicists studying heat radiation in their laboratories. You have geologists out in the Swiss Alps staring at enormous boulders sitting in the middle of valleys where they clearly don't belong, and scratches carved into bedrock that look like something massive and heavy dragged across the stone. And those geologists are starting to realize something that sounds absolutely wild when you first hear it. That vast sheets of ice, kilometers thick, once covered much of Europe and North America. That the Earth's climate had been radically, almost unimaginably different in the not-so-distant geological past. The person who pulled that idea together most forcefully was Louis Agassiz, a Swiss-born naturalist who, in 1837, stood before a meeting of the Swiss Society of Natural Sciences and proposed what he called a great ice period, an ice site, an ice age. And the reaction was not exactly warm. In fact, many of his colleagues were openly hostile. Here was this young naturalist, Agassiz was only 30 at the time, telling a room full of established scientists that their understanding of Earth's history was fundamentally incomplete. That enormous glaciers had once blanketed Switzerland, had ground down mountains, had carried boulders the size of houses, and deposited them hundreds of kilometers from where they started. And these scientists, many of whom had spent their careers explaining those same boulders and scratches through other theories, most commonly the idea that a great biblical flood had scattered debris across the landscape, were not thrilled to hear it. You have to understand, the dominant explanation at the time was diluvialism, the idea that Noah's flood, or something like it, had reshaped the surface of the earth. Those erratic boulders, carried by floodwaters, those scratches in the bedrock, scoured by rushing torrents. It was a tidy explanation. It had the weight of tradition behind it, and it didn't require you to imagine anything as outlandish as a continent buried under ice. So when Agassiz stood up and essentially said no, all of this evidence points to ice, not water, to glaciers that advanced and retreated over thousands of years. A lot of people pushed back, hard, but Agassiz was persistent, and more importantly, he was meticulous. He didn't just theorize. He went out into the field. He studied active glaciers in the Alps, measured their movement, documented how they carved the landscape in real time. He showed that the marks left by modern glaciers were identical to the mysterious scratches found on bedrock far from any existing ice. He traced the paths that ancient glaciers must have taken by following the trails of debris they left behind. Moraines, they're called. Those ridges of gravel and rock that glaciers push ahead of themselves like slow-motion bulldozers. And gradually, over the course of the 1840s and 1850s, the evidence became overwhelming. Other geologists went out and found the same patterns in Scotland, in Scandinavia, across New England. The signs were everywhere once you knew what to look for. By the 1870s, the Ice Age theory had gone from controversial to consensus. And here's what made it so important for climate science specifically. It proved, beyond any reasonable doubt, that Earth's climate was not stable, that it could change dramatically, that the world these scientists were living in, the mild, temperate, familiar world of 19th century Europe, was just one frame in a much longer movie. The planet had been radically colder. Glaciers had reached as far south as present-day London, had covered what is now Chicago under ice more than a kilometer thick. And then the ice had retreated. The climate had warmed. And the question that naturally followed, the question that connects the geologists to the physicists, that ties Agassiz to Fourier and Tyndall, was, why? What caused the ice to advance? What caused it to retreat? What controls these enormous swings in Earth's temperature? Now, One of the first people to seriously tackle that question from a mathematical standpoint was a Scottish scientist named James Kroll. And Kroll's story is one of my favorites in all of climate science because his background was so unlikely. He was born in 1821 in Perthshire, Scotland, to a poor family. He had almost no formal education. He worked as a carpenter, a tea merchant, an insurance salesman. He tried all sorts of things, and none of them really stuck. What he did have was an insatiable appetite for reading and thinking. He was self-taught in physics and mathematics, and he spent years working through problems on his own in whatever spare time he could find. In 1859, the same year Tyndall was doing his infrared experiments in London, Kroll took a job as a janitor at the Andersonian University in Glasgow. And the reason he took the job by his own account wasn't the pay, which was minimal. It was because the university had a library. He wanted access to books. So here's this janitor, mopping floors during the day and spending his evenings reading everything he can get his hands on about astronomy, geology, physics. And he starts thinking about what might cause ice ages. Kroll's insight was astronomical. He knew that Earth's orbit around the sun isn't a perfect circle. It's an ellipse, and the shape of that ellipse changes over time. Sometimes the orbit is more circular. Sometimes it's more elongated. This is called orbital eccentricity, and it varies on cycles of roughly 100,000 years. Kroll also knew that Earth's axis is tilted, and that tilt is what gives us seasons. But the tilt wobbles, and the orientation of the tilt relative to the elliptical orbit shifts over time, a phenomenon called the precession of the equinoxes, which cycles over about 26,000 years. What Kroll proposed in a series of papers starting in the 1860s was that these orbital variations could change how much sunlight different parts of Earth received at different times of year. And when the conditions were right, when winters in the northern hemisphere were particularly long and cold, snow and ice could accumulate year after year, building up into those massive ice sheets that Agassiz had described. It was a beautiful idea, elegant, grounded in celestial mechanics that were well understood, and it got a lot of attention. Kroll went from being a janitor to being elected a Fellow of the Royal Society, which is about as dramatic a career turnaround as science has ever seen. But here's the thing. When geologists started trying to match Kroll's predicted ice age timing to the actual geological evidence, the fit wasn't great. The dates didn't line up well, and by the time Kroll died in 1890, his theory had largely fallen out of favor. Most scientists figured the orbital idea was interesting, but probably wrong. It would take another half-century and a Serbian mathematician named Milutin Milanković to rescue and refine the orbital theory. But we'll get to Milanković a bit later. What matters right now is the question that was hanging in the air by the late 1800s. You've got this clear evidence that Earth's climate has changed enormously in the past, and you've got this laboratory proof that certain gases in the atmosphere can trap heat. And someone is going to connect those two threads explicitly. Someone is going to ask, could changes in the amount of carbon dioxide in the atmosphere be responsible for ice ages? That someone was Svante Arrhenius. And if you recognize that name, it's probably from chemistry class, not climate science. Arrhenius was a Swedish chemist, brilliant, stubborn, eventually won the Nobel Prize in Chemistry in 1903 for his work on electrolytes. But in the mid-1890s, he got interested in a different problem. He wanted to know whether changes in atmospheric carbon dioxide could explain the ice ages. And to answer that question, he did something extraordinary. He sat down and, by hand, calculated how much Earth's temperature would change if you doubled or halved the amount of carbon dioxide in the atmosphere. Think about what that means. This is 1896. There are no computers. There are no calculators in any modern sense. Arrhenius is working with pencil and paper, using data on how carbon dioxide and water vapor absorb infrared radiation at different wavelengths, breaking Earth's surface into latitude bands, accounting for the different angles at which sunlight strikes the surface at different latitudes, considering day and night, considering seasons. He later said the calculations took him over a year of tedious work, thousands of individual computations. His colleague Arvid Högbohm had suggested that volcanic emissions and weathering of rocks could change CO2 levels over geological time, and Arrhenius seized on that idea as a mechanism. If volcanoes pump CO2 into the air, and chemical weathering of rocks slowly removes it, then over millions of years, the concentration could rise and fall substantially. And when Arrhenius finished his calculations, he arrived at a number that is, frankly, astonishing in its accuracy. He estimated that doubling the concentration of carbon dioxide in the atmosphere would raise Earth's average temperature by about 5 to 6 degrees Celsius. The modern best estimate, after more than a century of additional research and the most powerful computers ever built, is somewhere around 2.5 to 4 degrees Celsius, with a best estimate near 3. Arrhenius was in the right ballpark, with pencil and paper, in 1896. Now he got some things wrong. His treatment of how clouds and water vapor would respond was simplified. He didn't fully account for the way the atmosphere moves heat around through convection and wind patterns. But the core insight was sound. Carbon dioxide is a control knob for Earth's temperature, and if you change it enough, you change the climate. Arrhenius even speculated about what would happen if industrial burning of coal continued to add CO2 to the atmosphere. But here's the part that surprises people. He thought it would be a good thing. He was Swedish. He lived through long, dark, cold winters. The idea of a warmer world sounded pleasant to him. He imagined future generations enjoying milder climates and better harvests. He had no concept of the scale or speed at which fossil fuel burning would accelerate in the 20th century. Arrhenius published his findings in 1896 in a paper called On the Influence of Carbonic Acid in the Air upon the Temperature of the Ground. Carbonic acid being the old term for carbon dioxide. And the paper was received with interest, but not universal acceptance. In fact, within a few years, a serious objection was raised that would haunt climate science for decades. The objection came from a Swedish physicist named Knut Ångström, and the argument went like this. Laboratory measurements seem to show that carbon dioxide already absorbed all the infrared radiation it could at the wavelengths where it operates. In other words, the absorption was already saturated. Adding more CO2, the argument went, wouldn't make any difference, because the existing CO2 was already catching all the heat it could. It would be like adding more paint to a wall that's already completely covered. Another coat doesn't change the color. This saturation argument was powerful, and it was persuasive. And for the first few decades of the 20th century, most physicists accepted it. The greenhouse effect of CO2 was considered a solved and closed question. Interesting historically, but not relevant to the real climate. If you were a scientist in, say, 1920 or 1930, and someone brought up the idea that carbon dioxide could change the climate, you would probably have dismissed it. The smart money said the effect was saturated. Case closed. Except it wasn't closed. The saturation argument had a flaw. A subtle, important flaw that wouldn't be fully understood until the 1940s and 1950s. and untangling that flaw required thinking about the atmosphere not as a single slab of gas sitting on the ground, but as a tall column, a vertical stack of layers, each at a different temperature and pressure, each absorbing and re-emitting radiation in complex ways. The key figure in cracking this problem was a Canadian-born physicist and engineer named Guy Stewart Callendar. Though calling him just a physicist doesn't really capture who he was. Callendar was a steam engineer by profession. He worked on problems of fuel efficiency and power generation. But climate was his passion, his obsession, the thing he spent his evenings and weekends on. And in 1938, he stood before the Royal Meteorological Society in London and presented a paper that would eventually reshape everything. What Callendar did was painstaking and, in its own quiet way, revolutionary. He gathered temperature records from weather stations around the world, hundreds of them, and showed that global temperatures had been rising since the late 19th century. This was the first time anyone had compiled enough data to demonstrate a clear warming trend. And then he connected that warming trend to the measured increase in atmospheric carbon dioxide from fossil fuel burning. He argued that the CO2 increase was real, that the warming was real, and that one was causing the other. The reaction was skeptical. The assembled meteorologists raised the saturation objection. They questioned his temperature data. They pointed out that natural variability could explain the warming. And Callendar, who was not a professional climate scientist, who was essentially an amateur pursuing this in his spare time, pushed back calmly and methodically. He had done his homework. He understood the radiation physics better than most of his critics, but he couldn't fully answer the saturation argument. Not yet. The tools to do so didn't quite exist. What Callendar did accomplish, though, was something crucial. He put the CO2 climate connection back on the table. He forced people to take it seriously again, even if they weren't convinced. And he coined a term for the warming effect of industrial carbon dioxide emissions that stuck around for a while: the Callendar effect. He kept publishing, kept refining his data, kept arguing his case through the 1940s and into the 1950s. And meanwhile, the technology that would finally settle the saturation debate was being developed in an unlikely place: the United States military. Because during and after World War II, the Air Force had a very practical problem. They needed to understand exactly how infrared radiation moved through the atmosphere, because it affected the performance of heat-seeking missiles and infrared sensors. And that military research would end up cracking the saturation problem wide open, in a way that nobody, certainly not the military researchers themselves, had originally intended. Here's what was going on. During World War II, and especially in the years right after, the U.S. Air Force poured money into understanding how infrared radiation behaves in the atmosphere. This wasn't about climate. This was about weapons. If you're designing a heat-seeking missile, you need to know exactly which wavelengths of infrared energy can travel through the air and which ones get absorbed before they reach the target. If the atmosphere swallows the specific wavelength your missile sensor is tuned to, your missile is blind. So the military funded very detailed, very precise laboratory measurements of exactly how different gases absorb infrared radiation at different wavelengths, different pressures, and different temperatures. They needed this data to be accurate. Lives depended on it. And the person who would take that military-funded research and turn it into a revolution in climate science was a physicist at the Air Force Cambridge Research Laboratories named Gilbert Plass. Plass was working on exactly this kind of infrared transmission problem in the early 1950s, and he had access to something that Arrhenius and Callendar never did: detailed high-resolution absorption spectra for carbon dioxide and water vapor. Not the rough, blurry measurements that Ångström had used back in 1900. These were precise, line-by-line measurements that showed exactly which narrow bands of infrared each gas absorbed and how strongly. And here's the thing. When Plas looked at the data carefully, the saturation argument fell apart. Remember, the saturation objection said that CO2 already absorbs all the infrared radiation it can at the wavelengths where it operates, so adding more CO2 wouldn't make any difference. It's like saying, well, the sponge is already soaked. Adding more sponge won't soak up more water. But that analogy was wrong, and Plas could now show exactly why. The key insight is this: the atmosphere isn't a single slab. It has layers. And what matters isn't just whether CO2 absorbs infrared radiation, it's where in the atmosphere the final absorption and re-emission happens. Think about it this way. The ground radiates infrared energy upward. CO2 molecules in the lower atmosphere absorb that energy, but then they re-emit it, some upward, some downward, some sideways. The energy that goes upward gets absorbed by CO2 molecules higher up. They re-emit it again. This keeps happening, layer by layer, all the way up through the atmosphere. Eventually, at some altitude, the atmosphere becomes thin enough that the infrared radiation can finally escape to space without being reabsorbed. That altitude, the effective emission height, is where Earth actually radiates its heat away. Now here's what's really clever about Plas's argument. If you add more CO2 to the atmosphere, you don't change what happens at the surface. The saturation crowd was right that the lower atmosphere is already opaque at CO2's main absorption wavelengths. But you do change the altitude at which the atmosphere becomes transparent enough for energy to escape. You push that effective emission height higher, and higher in the atmosphere means colder. A colder emitting layer radiates less energy to space. Less energy leaving means the planet warms up until a new balance is reached. The sponge analogy was wrong because it imagined a single sponge. The atmosphere is more like a stack of sponges, and adding CO2 is like adding more sponges on top. The bottom ones were already saturated, sure, but the new ones on top change where the last absorption happens, and that changes everything. Plas published a landmark paper in 1956. Actually, he published several papers around that time, arguing that doubling atmospheric CO2 would warm the Earth by about 3.6 degrees Celsius. That number is remarkably close to the middle of the range that modern climate models give us today. He also pointed out something that Callendar had been saying, that human fossil fuel burning was increasing CO2 levels and that this would cause measurable warming over the coming century. Plas was one of the first scientists to explicitly warn that this was a problem, not a benefit. Where Arrhenius had cheerfully imagined Scandinavians enjoying warmer winters, Plas was more cautious. He understood that rapid warming could be disruptive. But Plas didn't fully solve the problem either. His calculations, while much better than anything before, still had significant uncertainties. He didn't properly account for the role of the oceans in absorbing CO2, and he didn't fully handle the overlap between CO2 and water vapor absorption bands. Other scientists pointed these issues out, and for a while, the debate continued. But the direction was set. The saturation argument was mortally wounded, even if it took another decade or so to fully die. And this is where another figure enters the story, someone who might be the single most important person in the history of climate science that most people have never heard of. His name was Roger Revelle, and he was an oceanographer at the Scripps Institution of Oceanography in La Jolla, California. Revelle was a big personality, tall, charismatic, politically connected, the kind of scientist who could walk into a senator's office and make a compelling case for funding. He'd served in the Navy during World War II, doing oceanographic research, and afterward he helped build Scripps into one of the premier ocean research institutions in the world. And in the mid-1950s, Revelle got interested in a question that was central to the CO2 debate. What happens to the carbon dioxide that humans pump into the atmosphere? Does it stay there, or does the ocean absorb it? This was a critical question. If the ocean quickly absorbed most of the CO2 that humans emitted, then atmospheric concentrations wouldn't rise much, and warming wouldn't be a concern. A lot of scientists assumed this was the case. The ocean is enormous after all, and CO2 dissolves in water. It seemed reasonable that the ocean would act as a giant buffer, soaking up our emissions almost as fast as we produced them. Revelle, working with a chemist named Hans Suess, showed that this assumption was wrong. Or rather, it was far more complicated than people thought. They published a paper in 1957 that explained something counterintuitive about ocean chemistry. Yes, CO2 dissolves in seawater, but the chemistry of carbonate equilibrium in the ocean means that the surface water can't just absorb unlimited amounts of CO2. When CO2 dissolves in seawater, it forms carbonic acid, which reacts with carbonate ions already in the water. This reaction actually limits how much additional CO2 the surface ocean can take up. Revelle described it with a concept that became known as the Revelle factor. The ocean's surface layer would absorb some CO2, but much less than you'd naively expect. The deep ocean could absorb more, but mixing between the surface and the deep ocean is slow. It takes centuries for surface water to sink and be replaced by deep water. The implication was stark. A significant fraction of the CO2 that humans emitted would stay in the atmosphere for a long time. Revelle and Suess wrote a line in their 1957 paper that became one of the most quoted sentences in climate science history. They said that human beings were carrying out a large-scale geophysical experiment that could not be reproduced and should not be neglected. Think about that phrase for a second. A large-scale geophysical experiment. We were, in effect, running an uncontrolled experiment on the only planet we have, and nobody was systematically measuring what was happening. And that realization, that we were changing the atmosphere and we didn't even have good measurements of how fast, led directly to one of the most important scientific programs ever initiated. Revelle arranged for a young geochemist named Charles David Keeling to set up a continuous CO2 monitoring station. Keeling was meticulous, almost obsessively so. He'd already been measuring CO2 in the air around California and had noticed that background levels were remarkably consistent once you got away from local pollution sources. He had a gift for precision measurement and an almost stubborn insistence on getting the numbers right. With Revelle's support and funding that came partly through the International Geophysical Year of 1957 to 58, this massive international scientific collaboration that also launched the first satellites, Keeling set up his monitoring station at the Mauna Loa Observatory in Hawaii. The location was brilliant. Mauna Loa is a volcano on the Big Island, and the observatory sits at about 11,000 feet elevation, far above the local vegetation and weather patterns that could contaminate readings. The air that reaches it has traveled thousands of miles over the open Pacific. It's about as close to a clean, well-mixed sample of the global atmosphere as you can get. Keeling started taking measurements in March 1958, and almost immediately, he noticed something beautiful and something alarming. The beautiful thing was a seasonal cycle. Every year, CO2 levels dropped during the Northern Hemisphere spring and summer as plants grew and photosynthesis pulled carbon dioxide out of the air, and then rose again in fall and winter as plants died back and decomposition released CO2. It was like watching the planet breathe, one long inhalation and exhalation every year. The Northern Hemisphere dominates this cycle because that's where most of the world's land mass and vegetation is. But underneath that seasonal breathing, there was a trend. Year after year, the baseline was rising. Each spring's low point was higher than the previous spring's low point. Each winter's peak was higher than the last. The overall concentration was going up, steadily and unmistakably. When Keeling started measuring in 1958, the concentration was about 315 parts per million. Within just a few years, the upward trend was clear. And it has never stopped. It has never even paused. That record, the Keeling curve, as it came to be called, is one of the most important datasets in all of science. It's still being maintained today at the same observatory, using methods that Keeling himself established. As of recent years, the concentration has passed 420 parts per million and continues to climb. The Keeling curve did something that no theoretical argument could do on its own. It provided direct, continuous, irrefutable evidence that atmospheric CO2 was increasing. You could argue about models. You could argue about temperature records, but you couldn't argue with a direct measurement of the air, taken with careful calibration, day after day, year after year, showing the same relentless upward march. Keeling fought for decades to keep that monitoring program funded. It was constantly under threat from budget cuts, because continuous monitoring isn't glamorous science. It doesn't produce splashy breakthroughs. It's just someone carefully measuring the same thing over and over. But Keeling understood that the value of the record grew with every passing year. Each additional year of data made the trend more certain, the seasonal patterns more clear, the connection to fossil fuel emissions more undeniable. And while Keeling was building his curve, the theoretical side of climate science was advancing too. In the late 1950s and into the 1960s, scientists began using something that had barely existed a decade earlier: digital computers. And this is where the story takes another turn, because the question of how much warming you'd get from doubling CO2 is not something you can answer with a back-of-the-envelope calculation. The atmosphere is fantastically complex. It has layers. It has convection. It has clouds. Water vapor responds to temperature, creating feedbacks. The surface is part ocean and part land, with different properties. To really answer the question, you need to build a mathematical model of the entire atmosphere and run it forward in time. The first person to do this in a rigorous way was a Japanese-born meteorologist working at the Geophysical Fluid Dynamics Laboratory in Princeton, New Jersey. His name was Tsukuro Manabe, and he was about to change everything. Manabe arrived in the United States in 1958, the same year Keeling started his measurements on Mauna Loa, and there's something poetic about that timing. Two men, working on opposite sides of the country, one painstakingly measuring the real atmosphere, and the other trying to build a virtual one inside a machine. Manabe came from the University of Tokyo, where he'd studied meteorology, and he was recruited by Joseph Smagorinsky, who was setting up the Geophysical Fluid Dynamics Laboratory, the GFDL, as a place where the new power of digital computers could be applied to understanding weather and climate. And Manabe turned out to be exactly the right person for the job, because he had this remarkable ability to see which parts of a problem were essential and which parts you could set aside, at least for now. Here's the thing about modeling the atmosphere. If you try to include everything, every cloud, every ocean current, every mountain range, every feedback, you'll never finish. The problem is too big, even for a computer. Especially for the computers they had in the early 1960s, which were, by today's standards, laughably slow. We're talking about machines with less computing power than the phone in your pocket. Way less. So Manabe made a brilliant simplifying decision. Instead of trying to model the entire three-dimensional atmosphere of the whole Earth, he started with a single column of air. Just one vertical column, stretching from the surface up to the top of the atmosphere. He divided it into layers and asked a deceptively simple question. If you set the composition of this column, the amount of CO2, the amount of water vapor, the incoming solar energy, and let it reach equilibrium, what temperature profile do you get? Now, this might sound too simple to be useful, but that's what made Manabe so clever. He included the things that really matter. He included radiative transfer, how infrared radiation moves up and down through the atmosphere, being absorbed and re-emitted by greenhouse gases at different altitudes. He included convection, because in the real atmosphere, when the lower layers get too warm, air rises and carries heat upward. If you leave convection out, your model produces a surface temperature that's way too hot and an upper atmosphere that's way too cold. Manabe handled this with what's called a convective adjustment. Basically, whenever the temperature difference between layers got too steep, he'd redistribute the heat to mimic the effect of rising air. It's an approximation, but it's a physically grounded one. And here's the really important part. He included water vapor feedback. Remember, water vapor is actually the most powerful greenhouse gas in the atmosphere. Tyndall figured that out back in the 1860s. But water vapor is different from CO2 in a crucial way. Humans don't directly control how much water vapor is in the atmosphere. The amount of water vapor is controlled by temperature. Warmer air holds more moisture. That's basic physics, described by something called the Clausius-Clapeyron relation. So if you add CO2 and the atmosphere warms a little, that warming allows the air to hold more water vapor, which is itself a greenhouse gas, which causes more warming, which allows more water vapor, and so on. It's a positive feedback loop, and Manabe built this into his model. He assumed that as temperature changed, the relative humidity, the percentage of maximum moisture the air could hold, would stay roughly constant, which means that as things warm up, the absolute amount of water vapor increases. This assumption turned out to be remarkably accurate. Decades of satellite observations have confirmed that relative humidity does stay roughly constant as the climate warms. So in 1967, Manabe and his colleague Richard Weatherald published their results. They ran their column model with the current level of CO2, and it produced a temperature profile that matched the real atmosphere pretty well. Then they doubled the CO2 and let the model reach a new equilibrium. The result? The surface warmed by about 2.3 degrees Celsius. Now, think about what that number means in context. Arrhenius, back in 1896, working with pencil and paper and logarithm tables, had estimated about 5 to 6 degrees for a CO2 doubling, though he later revised it down to around 4. Plass, in 1956, had gotten about 3.6 degrees. And now Manabe, with the most sophisticated model yet built, was getting 2.3 degrees. These numbers aren't identical, but they're all in the same ballpark. And the fact that they're in the same ballpark, despite using completely different methods, that's actually really significant. It suggests there's a real, robust physical signal here. The differences come down to which feedbacks you include and how you handle them. Manabe's 2.3 degrees was for a relatively simple model without ice albedo feedback, the effect where warming melts ice, exposing darker ocean or land, which absorbs more sunlight, which causes more warming. When you add that in, the number goes up. And Manabe didn't stop with the single column. Through the late 1960s and into the 1970s, he and Smagorinsky and their colleagues at GFDL built increasingly sophisticated models. They went from 1 dimension to 3. They created what we now call general circulation models, or GCMs, full 3-dimensional simulations of the atmosphere, divided into grid cells covering the whole globe, with equations governing how air moves, how heat flows, how moisture evaporates and condenses. These were the ancestors of the climate models we use today, and every time they ran the experiment, double the CO2 and see what happens, they got warming. The exact number varied depending on the model's details, but it kept coming back to that same general range. A few degrees Celsius for a doubling of CO2. Now, while Manabe was building his models in Princeton, something else was happening in the broader scientific community. The temperature record, the actual measured temperature of the Earth's surface, was doing something confusing. From about the 1940s through the early 1970s, global temperatures had been roughly flat or even declining slightly. And this created a real puzzle, because CO2 was clearly going up. Keeling's curve showed that, but temperatures weren't following. Some scientists started wondering if the warming effect of CO2 was being masked by something else. And they were right. But the something else turned out to be complicated. Part of the answer was aerosols, tiny particles suspended in the atmosphere, produced by industrial pollution, volcanic eruptions, and other sources. Sulfate aerosols, in particular, which come from burning coal and oil, have a cooling effect. They reflect sunlight back to space before it can warm the surface, and they also change the properties of clouds in ways that tend to cool things. So during the mid-20th century, as the industrial world was burning enormous amounts of coal with very little pollution control, it was simultaneously pumping CO2 into the atmosphere, which warms, and sulfate aerosols, which cool. The two effects were partially canceling each other out. It's like pressing the gas and the brake at the same time. This is where things got a bit messy in the public conversation. In the early 1970s, a few scientists and a lot of journalists picked up on the cooling trend and ran with it. There were magazine covers and newspaper articles asking whether we were heading into a new ice age. And this is one of those moments in the history of climate science that gets brought up constantly, usually by people trying to discredit climate science. They predicted an ice age in the 1970s, and they were wrong, so why should we believe them now? But here's what actually happened. If you go back and look at the scientific literature from that period, and people have done this systematically, the overwhelming majority of climate papers in the 1970s that made projections about future temperature predicted warming, not cooling. The Ice Age scare was primarily a media phenomenon, not a scientific consensus. There were a handful of scientists who took the cooling trend seriously and speculated about its continuation, and their papers got outsized attention. But the mainstream of the field, the people doing the modeling work, the people who understood the radiative physics, they knew that CO2 was the bigger long-term forcing. And speaking of long-term forcing, this is a good moment to circle back to something we touched on earlier, the ice ages and what actually causes them. Remember James Kroll, the self-taught Scotsman who proposed that changes in Earth's orbit could trigger ice ages? His specific mechanism didn't work out, but the basic idea that orbital variations matter, was picked up and refined by a Serbian mathematician named Milutin Milanković. Working in the early 20th century, Milanković spent decades, literally decades, calculating how 3 different orbital cycles affect the amount of solar energy hitting different parts of the Earth at different times of year. There's the eccentricity of Earth's orbit, which is how elliptical it is, cycling over about 100,000 years. There's the obliquity, the tilt of Earth's axis, which varies between about 22 and 24.5 degrees over a roughly 41,000-year cycle. And there's precession, the wobble of the axis, with a cycle of about 26,000 years. Milanković calculated that the key factor wasn't the total amount of sunlight Earth receives. That barely changes, but how it's distributed. Specifically, what matters is how much summer sunshine falls at high northern latitudes, around 65 degrees north. If summers there are cool enough that winter snow doesn't fully melt, the snow accumulates year after year, building into ice sheets. The ice reflects more sunlight, cooling things further, and you get a feedback loop that plunges the planet into a glacial period. Milanković published his theory in the 1920s and 1930s, but for decades it was controversial because nobody had a good enough record of past ice ages to test it against. That changed in 1976 when James Hayes, John Embry, and Nicholas Shackleton published a landmark paper called Variations in the Earth's Orbit, Pacemaker of the Ice Ages. They analyzed deep-sea sediment cores, long cylinders of mud pulled up from the ocean floor, containing the shells of tiny organisms called foraminifera. The chemical composition of those shells, specifically the ratio of oxygen 18 to oxygen 16, acts as a thermometer for past ocean temperatures. And when they analyzed the frequency of temperature variations over hundreds of thousands of years, they found exactly the periodicities Milanković had predicted. The 100,000-year cycle, the 41,000-year cycle, the 26,000-year cycle, all right there in the data. It was a stunning confirmation. But here's what's really interesting about the Milanković cycles in the context of CO2 and climate. When scientists later extracted ice cores from Antarctica and Greenland, drilling down through kilometers of ancient ice that trapped tiny bubbles of ancient atmosphere, they found that CO2 levels and temperature moved in lockstep through the ice ages. During glacial periods, CO2 dropped to around 180 parts per million. During warm interglacials, it rose to about 280. And the orbital cycles were the initial trigger, the pacemaker, but CO2 acted as a crucial amplifier. A small orbital nudge would start warming at high latitudes, which would cause the oceans to release some dissolved CO2, which would enhance the greenhouse effect, which would cause more warming, which would release more CO2. The same feedback worked in reverse during cooling. So the ice ages were a beautiful, terrifying demonstration of exactly the kind of CO2 temperature feedback that climate scientists were warning about. The planet had run this experiment before, naturally, over and over, and the answer was always the same. More CO2 means warmer, less CO2 means colder. And this brings us to a critical moment in the late 1970s when the U.S. government started paying serious attention. In 1979, the National Academy of Sciences convened a panel to assess the state of climate science. It was chaired by Jules Charny, one of the most respected meteorologists in the world, the man who had essentially founded modern numerical weather prediction. Charny gathered a group of top scientists, reviewed the models, reviewed the physics, and asked a deceptively simple question. If you double the amount of carbon dioxide in the atmosphere, how much warmer does the Earth get? And the answer his panel arrived at, after weeks of careful deliberation, was somewhere between 1.5 and 4.5 degrees Celsius, with a best estimate of about 3 degrees. That range, 1.5 to 4.5, is one of the most remarkable numbers in all of science, and I want you to sit with it for a moment. Because here we are, more than 4 decades later, and the range has barely budged. The most recent major assessment, published in 2021, narrowed it slightly to 2.5 to 4 degrees, with a best estimate of 3. But the basic answer that Charney's panel gave in 1979 has held up through decades of vastly more sophisticated modeling, satellite observations, paleoclimate data, and computational power that would have seemed like science fiction to Charney and his colleagues. That kind of durability in a scientific estimate is extraordinary. It tells you that the underlying physics was already well understood. The Charney report, as it came to be known, was clear and unequivocal. It said, essentially, we have tried to find a way to make this problem go away, and we can't. The physics is solid, the models agree. If CO2 keeps rising, the planet will warm significantly. And what's striking about reading the report today is how measured and careful the language is, but also how direct. There's no hedging, no, maybe it's natural variability, no escape hatch. Charney and his panel looked at the science from every angle they could think of, considered every objection, and concluded that the greenhouse effect was real, quantifiable, and consequential. Now, you might think that a report like that from the most prestigious scientific body in the United States would have triggered immediate action. But of course, that's not what happened. And to understand why, you have to understand the political and economic landscape of the late 1970s and 1980s. The world was in the middle of an energy crisis. Oil prices had spiked dramatically after the 1973 OPEC embargo, and again after the 1979 Iranian Revolution. Economies were staggering. Inflation was rampant. The idea of voluntarily constraining fossil fuel use, the very thing that powered modern civilization, was, to put it mildly, a hard sell. And so the Charney report was received with respect in scientific circles, acknowledged by policymakers, and then largely set aside while more pressing economic concerns took priority. But the science didn't stop. And this is where the story gets both fascinating and, honestly, a little heartbreaking, because through the 1980s, the evidence kept accumulating, and a handful of scientists kept pushing to make the world pay attention. One of those scientists was James Hansen. And if you're going to understand the modern history of climate science, you really need to know about Hansen, because he's one of the most consequential and controversial figures in this entire story. Hansen was a physicist at NASA's Goddard Institute for Space Studies, which everyone just calls GSS. It's located improbably above a restaurant on Broadway in New York City. Not exactly what you picture when you think of NASA. Hansen had originally studied the atmosphere of Venus, that hellish planet where a runaway greenhouse effect had turned the surface into a 460 degrees Celsius furnace, hot enough to melt lead. So when he turned his attention to Earth's atmosphere, he came at it with a deep, almost visceral understanding of what greenhouse gases could do when they accumulated without limit. Hansen built his own climate model at GISS, independent of the one at GFDL that Manabe had been developing. And this is actually important. Having multiple independent modeling groups is crucial in science, because if two completely different teams using different approaches and different code arrive at similar answers, that's much more convincing than a single result. And that's exactly what happened. Hansen's model, like Manabe's, showed significant warming from doubled CO2, right in the range that the Charney report had identified. But Hansen did something that most climate scientists of his era were reluctant to do. He started making specific, testable predictions about the near future. In 1981, he and his colleagues published a paper in Science predicting that human-caused warming would rise above the noise of natural climate variability by the end of the 20th century. They predicted that the 1990s would be warmer than the 1980s, that the Arctic would warm faster than the tropics, that the stratosphere would cool even as the surface warmed, which is a distinctive fingerprint of greenhouse warming, by the way, because if the sun were causing the warming, you'd expect both the surface and the stratosphere to warm together, but greenhouse gases trap heat near the surface and actually cool the upper atmosphere by radiating more efficiently to space from up there. Every one of those predictions has since been confirmed. Then came 1988, and this is the year that climate change truly entered public consciousness. It was a brutally hot summer in the United States. Drought scorched the Midwest. The Mississippi River dropped so low that barge traffic was disrupted. Yellowstone National Park burned in massive wildfires. And on June 23rd, with temperatures in Washington, D.C. hitting 101 degrees Fahrenheit, James Hansen testified before the U.S. Senate Committee on Energy and Natural Resources. He said, plainly and directly, that he was 99% certain that the warming trend observed over the previous century was not natural variability. It was caused by the buildup of greenhouse gases. He said the greenhouse effect had been detected and was changing our climate now. It was a bombshell. The New York Times ran it on the front page. Suddenly, climate change was no longer an abstract scientific concern buried in technical journals. It was news. And Hansen's willingness to speak so directly, to put a number on his confidence, to say, "This is happening now," rather than hedging with the usual scientific caveats, it made him a hero to environmentalists and a target to critics. Some of his fellow scientists were uncomfortable with how far he'd gone. They thought he was being too definitive, too political. The scientific culture of the time valued caution and understatement. You were supposed to say, "The data suggest," and further research is needed, not, "I'm 99% certain." But Hansen felt that the science was clear enough and the stakes were high enough, that caution had become its own form of irresponsibility. And here's the thing. The 1988 testimony didn't happen in a vacuum. That same year, the United Nations established the Intergovernmental Panel on Climate Change, the IPCC. And this is an institution that has shaped the entire trajectory of climate science and climate policy ever since. So it's worth understanding what it is and how it works. The IPCC doesn't do original research. It doesn't run climate models or drill ice cores. What it does is assess the existing scientific literature, thousands upon thousands of peer-reviewed papers, and synthesize them into comprehensive reports that represent the state of knowledge at a given time. It was set up jointly by the World Meteorological Organization and the United Nations Environment Program, and its reports are written by hundreds of scientists from around the world, reviewed by hundreds more, and then approved line by line by government representatives. That last part is important. It means the final summary documents are, in a sense, negotiated texts, which makes them more conservative than the underlying science, not less. If anything, the IPCC tends to understate risks, because every sentence has to survive scrutiny from governments that may have economic reasons to downplay the problem. The IPCC released its first assessment report in 1990, and it confirmed what Charney had said a decade earlier. what Arrhenius had calculated almost a century before that, what Tyndall and Foote had demonstrated in their laboratories in the 1850s. Carbon dioxide warms the planet. Humans are adding carbon dioxide to the atmosphere at an unprecedented rate, and the consequences will be significant. The report projected warming of about 0.3 degrees Celsius per decade under a business-as-usual scenario, which would mean roughly 1 degree of warming by 2025 relative to pre-industrial levels. That projection has turned out to be remarkably close to what's actually happened. But the early 1990s also saw the emergence of organized opposition to climate science. And this is a part of the story that matters. Not because the scientific debate was genuinely in doubt, but because the public perception of that debate was deliberately manipulated. Fossil fuel companies, some of which had their own internal research confirming the reality of human-caused warming. Exxon's own scientists had been modeling climate change since the late 1970s and had reached conclusions consistent with the mainstream science, began funding campaigns to emphasize uncertainty, to amplify the voices of a small number of contrarian scientists, and to frame the issue as an unresolved debate rather than a settled question. The strategy was explicitly modeled on the tobacco industry's decades-long campaign to cast doubt on the link between smoking and cancer. Internal documents that later came to light showed that the goal was not to prove that climate change wasn't real, but simply to create enough doubt in the public mind to delay regulatory action. And it worked, at least for a while. Through the 1990s and into the 2000s, public understanding of climate science lagged far behind the scientific consensus. Polls showed that many people believed scientists were still divided on whether warming was happening and whether humans were causing it, even though the actual scientific community was increasingly unified. Meanwhile, the science kept advancing, and one of the most important developments of the 1990s was the growing ability to attribute specific changes in the climate system to human influence, to move beyond just saying it's warming to saying, here's the human fingerprint. This is called detection and attribution science, and it's genuinely clever. The idea is that different causes of climate change produce different patterns. Solar changes would warm the whole atmosphere uniformly. Volcanic eruptions produce short-term cooling after major events. Greenhouse gases produce a very specific pattern: surface warming, stratospheric cooling, greater warming at night than during the day, greater warming at high latitudes than low latitudes, greater warming over land than over ocean. And when scientists looked at the actual observed patterns of temperature change, they matched the greenhouse gas fingerprint, not the solar fingerprint, not volcanic patterns, not any natural explanation. This fingerprinting work culminated in a famous statement in the IPCC's second assessment report in 1995. The lead author of the detection chapter was Ben Santer, a climate scientist at Lawrence Livermore National Laboratory, and after exhaustive analysis, the report included the carefully worded conclusion that the balance of evidence suggests a discernible human influence on global climate. That single sentence, discernible human influence, was the first time an international scientific body had formally declared that humans were detectably changing the climate. And Santer paid a personal price for it. He was attacked viciously by contrarian groups, accused of scientific fraud, received death threats. His career and his personal life were disrupted for years. It's one of those stories that reminds you that science doesn't happen in some pristine, apolitical space. Real people put their names on these conclusions, and sometimes they suffer for it. But the evidence kept building. The third assessment report in 2001 strengthened the language. Warming was likely, meaning greater than 66% probability, due to human activities. The fourth assessment report in 2007 went further. Very likely, meaning greater than 90%. And the fifth assessment report in 2013 reached extremely likely, greater than 95%. Each report drew on more data, more models, more paleoclimate evidence, more observations from satellites and ocean buoys and weather stations around the world. The uncertainty wasn't growing. It was shrinking steadily and relentlessly, and it was shrinking in the direction of confirming what the physics had predicted all along. And during this same period, something else was happening that would transform climate science from a discipline focused primarily on temperature into something much broader and more urgent. Scientists were beginning to observe changes in the Earth system that went beyond what the early models had anticipated, changes that were happening faster than expected, in ways that raised entirely new questions about feedback loops, tipping points, and the sheer interconnectedness of systems that had previously been studied in isolation. Because here's the thing. For most of the 20th century, climate science was, at its core, a temperature problem. How much warming do you get from a given amount of CO2? That was the question Arrhenius asked, the question Manabe modeled, the question Charney's panel tried to bound. And it's an incredibly important question. But starting in the late 1980s and accelerating through the 1990s and 2000s, researchers began to realize that temperature was really just the opening act. The warming itself was setting off a cascade of physical changes across the planet, and some of those changes had the potential to accelerate the warming further, creating what scientists call positive feedback loops. Not positive in the sense of good, but positive in the engineering sense, meaning self-reinforcing. Let's talk about ice for a moment, because ice is where some of the most dramatic and frankly alarming observations started showing up. You remember the ice ages we talked about earlier, the Milankovitch cycles, the way tiny orbital wobbles got amplified into massive glacial advances and retreats. Well, one of the key amplifiers in that process was something called ice albedo feedback, and it's beautifully simple to understand. Albedo is just a measure of how reflective a surface is. Fresh snow and ice are incredibly reflective. They bounce back something like 80 or 90% of the sunlight that hits them. Open ocean water, by contrast, is dark. It absorbs more than 90% of incoming sunlight. So when you warm the planet a little and some ice melts, you replace a bright, reflective surface with a dark, absorbing one. That means the surface absorbs more energy, which causes more warming, which melts more ice, which exposes more dark water, which absorbs more energy. You can see where this goes. It's a loop, and once it gets going, it feeds itself. Now, scientists had understood ice albedo feedback theoretically for a long time. It was built into the climate models. But what started happening in the real world, particularly in the Arctic, outpaced what the models had predicted. Arctic sea ice extent, the total area of ocean covered by ice, had been monitored by satellites since 1979, and through the 1980s and 1990s it was declining, but at a pace that seemed roughly consistent with model projections. Then, in the early 2000s, the decline accelerated. In September 2007, Arctic sea ice hit a record low that stunned the scientific community. It was so far below the previous record, set in 2005, that some researchers initially thought there must be an error in the satellite data. There wasn't. The ice had simply retreated faster than anyone had expected. The Northwest Passage, that fabled sea route through the Canadian Arctic that had defeated explorers for centuries, that had killed Sir John Franklin and his entire crew in the 1840s, was open water you could sail a boat through it. And that 2007 record was itself broken in 2012, when Arctic sea ice extent dropped to about 3.4 million square kilometers, roughly half of what the long-term average had been in the 1980s. Half. Gone in about 3 decades. The models had generally predicted that the Arctic might see ice-free summers sometime around the middle or latter part of the 21st century. Reality was running ahead of the projections by decades. This wasn't just an Arctic problem either. The great ice sheets, Greenland and Antarctica, were also behaving in ways that demanded attention. The Greenland ice sheet contains enough frozen water to raise global sea levels by about 7 meters if it all melted. Antarctica holds enough for roughly 58 meters. For most of the 20th century, these ice sheets were treated as essentially static features in climate models. Massive, ancient, slow to change. The assumption was that any significant melting would take centuries or millennia. But starting in the 1990s, satellite measurements and on-the-ground observations began telling a different story. In Greenland, researchers noticed that the ice sheet was losing mass not just from surface melting, which you'd expect as temperatures rise, but also from a process that was far more dynamic and harder to model. Outlet glaciers, the rivers of ice that flow from the interior of the ice sheet down to the coast, were speeding up. Jakobshavn Glacier, one of the largest and fastest-moving glaciers in Greenland, roughly doubled its speed between 1997 and 2003. It was calving enormous icebergs into the fjord at an accelerating rate. And the mechanism driving this acceleration turned out to be fascinating and a little terrifying. Warm ocean water was getting underneath the glacier, where it met the sea, melting the ice from below, undermining the glacier's grounding line, the point where the ice lifts off the bedrock and begins to float. As the grounding line retreated, the glacier lost its anchor, and the ice behind it flowed faster toward the ocean. This same process was observed in West Antarctica, particularly in the glaciers draining into the Amundsen Sea, Pine Island Glacier and Thwaites Glacier, sometimes called the Doomsday Glacier in the press, though scientists tend to avoid that kind of language. Thwaites is enormous, roughly the size of Florida, and it acts as a kind of cork, holding back a much larger volume of ice in the West Antarctic ice sheet. Observations from the 2000s and 2010s showed that warm circumpolar deep water was reaching the base of Thwaites, eroding it from below, and the grounding line was retreating at a rate of about 0.5 kilometer per year in some areas. The concern, and this is still an active area of research, is that the bedrock beneath West Antarctica slopes downward as you move inland, which means that as the grounding line retreats, it encounters ice that's thicker and sits on deeper bedrock, which could make the retreat self-sustaining. This is what glaciologists call marine ice sheet instability, and if it's triggered in a major way, it could contribute several meters of sea level rise over centuries, faster than civilizations have ever had to adapt to. And sea level rise itself turned out to be more complicated than early estimates suggested. For a long time, the primary driver of sea level rise was thermal expansion. Water expands as it warms, and the oceans had been absorbing the vast majority of the excess heat trapped by greenhouse gases. Something like 90% of the extra energy in the climate system goes into the ocean. That's an almost incomprehensible amount of energy. If you tried to quantify it, it would be equivalent to detonating several Hiroshima-sized atomic bombs per second, continuously, for decades. The ocean has been quietly absorbing all of that, which is why atmospheric warming has been as moderate as it has. But that absorption comes with consequences. The water expands, and sea levels rise. By the early 2000s, though, Ice sheet and glacier contributions to sea level rise were growing, and they were growing faster than thermal expansion. Tide gauge records going back to the 19th century showed that global sea levels had risen by about 15 to 20 centimeters over the 20th century. Satellite altimetry, which began in 1993, showed that the rate was accelerating from about 2.5 millimeters per year in the 1990s to over 3.5 millimeters per year by the 2010s. That might not sound like much, but think about what a few millimeters per year means over decades, compounded by acceleration. And think about what it means for low-lying coastal areas, for island nations, for cities like Miami and Jakarta and Dhaka and Shanghai. But the changes weren't limited to ice and oceans. The carbon cycle itself was showing signs of stress. Remember Roger Revell's insight that the ocean couldn't absorb CO2 as readily as people had assumed? Well, the ocean was absorbing a significant amount, roughly a quarter of human CO2 emissions, but that absorption was changing the chemistry of seawater in a way that nobody had really focused on until the early 2000s. When CO2 dissolves in water, it forms carbonic acid. More CO2 means more acid. Ocean pH had dropped by about 0.1 units since the pre-industrial era, which sounds tiny but represents roughly a 26% increase in hydrogen ion concentration because pH is a logarithmic scale. This process, ocean acidification, was sometimes called the other CO2 problem, and it threatened marine ecosystems in ways that had nothing to do with temperature. Coral reefs, shellfish, certain plankton species, organisms that build their shells and skeletons from calcium carbonate, were finding it harder to do so in more acidic water. And these weren't obscure organisms. Coral reefs support roughly a quarter of all marine species. The base of many ocean food chains depends on tiny calcifying plankton. Meanwhile, on land, ecosystems were responding to the warming in ways that ecologists could track. Spring was arriving earlier in many parts of the northern hemisphere, trees leafing out sooner, migratory birds arriving ahead of schedule, growing seasons lengthening. Permafrost, the permanently frozen ground that underlies vast stretches of Siberia, Alaska, and northern Canada, was beginning to thaw. And this was another one of those feedback loops that kept scientists up at night, because permafrost contains enormous quantities of organic carbon, dead plant material that's been frozen for thousands of years. As it thaws, microbes begin decomposing that material, releasing CO2 and methane into the atmosphere. Methane is a particularly potent greenhouse gas, molecule for molecule. It traps roughly 80 times more heat than CO2 over a 20-year period. The total amount of carbon locked in permafrost is estimated at roughly 1,500 billion metric tons, about twice the amount currently in the atmosphere. Not all of it would be released, and not quickly, but even a fraction would represent a significant additional source of warming that was entirely outside human control. And this is really the key insight that emerged from this period, roughly the late 1990s through the 2010s. Climate change wasn't just about the thermostat going up a degree or two. It was about the interconnected response of an entire planetary system, ice, oceans, ecosystems, the carbon cycle itself, to a perturbation that was geologically instantaneous. Humans had increased atmospheric CO2 by more than 40% in about 150 years. In geological terms, that's not even a blink. The last time CO2 levels were this high was during the Pliocene epoch, roughly 3 to 5 million years ago, when sea levels were perhaps 15 to 25 meters higher and the Arctic was forested. The Earth system hadn't had time to fully respond to the change we'd already made, let alone the additional emissions that were continuing to accelerate year after year. And it was during this period that a concept began to crystallize in the scientific literature that would reshape how policymakers and the public thought about the problem: the idea of a carbon budget. The logic was elegant and, in some ways, brutally simple. If you could estimate the total sensitivity of the climate system, how much warming you get per unit of cumulative CO2, then you could calculate how much more CO2 humanity could emit before crossing a given temperature threshold. And the threshold that emerged as a focal point was 2 degrees Celsius above pre-industrial levels. That number, 2 degrees, had actually been floating around for a while. You can trace it back to an economist named William Nordhaus, who mentioned it almost in passing in a 1975 paper, noting that a warming of 2 degrees would push the climate beyond anything experienced in the last several 100,000 years. It wasn't derived from some precise calculation of catastrophe. It was more of a rough boundary marker. Beyond this point, we're in truly uncharted territory. But over the decades, as the science matured and the evidence accumulated, that 2-degree figure took on a life of its own. It became a kind of guardrail in international negotiations, a line that diplomats and scientists could point to and say, "This is what we're trying to stay below." And the carbon budget gave that line real teeth, because it turned a temperature target into a tonnage limit. In 2009, a landmark paper by Mineshausen and colleagues in Nature quantified it with striking clarity. To have a reasonable chance, say a 2/3 probability, of staying below 2 degrees of warming, total cumulative CO2 emissions from the start of the industrial era could not exceed roughly 1 trillion metric tons of carbon, and by the time that paper was published, humanity had already burned through more than half of that budget. Think about what that means. All the coal burned since the steam engine, all the oil since Drake's well in Pennsylvania, all the natural gas, all the cement, all the deforestation. It had consumed over half the total budget, and the rate of spending was accelerating, not slowing down. Now, different research groups produced slightly different numbers depending on their assumptions about climate sensitivity, about other greenhouse gases, about aerosol cooling effects. But the basic picture was consistent and sobering. At the emission rates of the early 2000s, roughly 36 billion tons of CO2 per year from fossil fuels and industry alone, the remaining budget for 2 degrees would be exhausted in a matter of decades, not centuries. And for a more ambitious target, say 1.5 degrees, which small island nations and vulnerable countries argued was the real threshold for survival, the budget was even tighter. Almost gone, in fact. This framing, the carbon budget, was powerful because it cut through a lot of the complexity. You didn't need to understand radiative transfer, or ocean circulation, or ice sheet dynamics. You just needed to understand a checking account. There's a finite amount you can spend. Every ton of CO2 you emit is a withdrawal. When the account hits zero, you've committed to that level of warming. And the math was unforgiving. It didn't care about politics or economics or who was responsible for past emissions. It was just physics and arithmetic. And it was this framing that shaped the most significant climate agreement in history. In December 2015, representatives from 195 nations gathered in Paris for the 21st Conference of the Parties, COP21. The negotiations were intense, the stakes enormous. Previous attempts at binding global agreements had largely failed. The Kyoto Protocol of 1997 had been a partial success at best. The United States never ratified it. Major developing nations weren't bound by it, and global emissions had continued to climb. The Copenhagen Summit in 2009 had ended in near chaos, producing only a weak non-binding accord. So Paris carried the weight of all those failures. What emerged was the Paris Agreement, adopted on December 12, 2015. Its central goal was to hold the increase in global average temperature to well below 2 degrees Celsius above pre-industrial levels, and to pursue efforts to limit the increase to 1.5 degrees. That 1.5 degree aspiration was a late addition, pushed hard by the alliance of small island states, nations like Tuvalu and the Marshall Islands, for whom even 2 degrees of warming could mean existential sea level rise. The agreement worked through nationally determined contributions. Each country would set its own emission reduction targets, report on progress, and ratchet up ambition over time. It wasn't a top-down mandate. It was a bottom-up pledge system, which was both its political genius and its structural weakness. Here's the thing about Paris, though. Even at the time, scientists were clear that the pledges on the table, the sum of all the national commitments, fell far short of what was needed. If every country met its Paris pledge, the world was still on track for roughly 2.7 to 3 degrees of warming by 2100. The agreement was a framework, a direction, a signal to markets and governments. But the gap between ambition and action was enormous. And meanwhile, the science kept moving. In 2018, the IPCC released a special report specifically on the 1.5 degree target, and it landed like a thunderclap. The report laid out in meticulous detail the differences between a 1.5 degree world and a 2 degree world. At 2 degrees, virtually all tropical coral reefs would be lost. At 1.5, maybe 10 to 30% could survive. At 2 degrees, Arctic summers without sea ice might happen once per decade. At 1.5, perhaps once per century. The half-degree difference between those two targets, which sounds trivial when you say it quickly, translated into dramatically different outcomes for hundreds of millions of people. More extreme heat, more intense rainfall, greater crop failures, more species loss, higher seas. The report concluded that limiting warming to 1.5 degrees would require cutting global CO2 emissions by about 45% from 2010 levels by 2030 and reaching net zero by around 2050. Net zero. That phrase entered the mainstream vocabulary around this time, and it's worth pausing on what it actually means. Net zero doesn't necessarily mean emitting no CO2 at all. It means that whatever CO2 you do emit is balanced by an equal amount being removed from the atmosphere through forests, soil, direct air capture, or other means. It's a balance sheet, and reaching it by 2050 would require what the IPCC called rapid, far-reaching, and unprecedented changes in all aspects of society: energy, transportation, industry, agriculture, buildings. Everything would need to transform within a single generation. Now, there's something remarkable about where the science stood by this point. Think back to where we started this whole story. Fourier puzzling over why the Earth was warmer than bare calculations predicted, Foote holding glass jars in the sun, Tyndall in his basement lab with his spectrophotometer. The fundamental physics hadn't changed. CO2 absorbs infrared radiation. More CO2 means more absorption, means a warmer surface. That basic chain of reasoning, established in the 1850s and 1860s, had survived over a century and a half of testing, refinement, and elaboration. What had changed was the resolution, the ability to see the full complexity of the system, to model the feedbacks, to measure the consequences in real time. By the late 2000s and into the 2020s, climate science had entered what you might call its observational golden age. Satellites like NASA's GRACE mission, Gravity Recovery and Climate Experiment, could measure the mass of ice sheets by detecting tiny changes in Earth's gravitational field. Think about that for a second. You're weighing Greenland from space, essentially, by flying twin satellites in formation and measuring how the distance between them changes as they pass over regions with more or less mass beneath them. And what Grace showed was unambiguous. Greenland was losing roughly 280 billion tons of ice per year by the 2010s. Antarctica was losing about 150 billion tons per year. These weren't model projections. They were measurements. Ocean heat content was being tracked by the Argo network, nearly 4,000 autonomous floats distributed across the world's oceans, each one diving to depths of 2,000 meters, measuring temperature and salinity as it rose, then transmitting the data via satellite before diving again. The picture from Argo was striking. The oceans had absorbed more than 90% of the excess heat trapped by greenhouse gases. That's a number worth sitting with. More than 90%. The atmosphere, the land surface, the ice, all of that warming we could see and feel, represented less than 10% of the total energy imbalance. The oceans were doing the heavy lifting, absorbing heat that would otherwise have made surface warming far more dramatic. But that absorption came with consequences: thermal expansion raising sea levels, marine heat waves devastating ecosystems, disrupted circulation patterns. And then there were the attribution studies, which had become remarkably sophisticated. For decades, skeptics had argued that you couldn't link any individual weather event to climate change. And for a while, that was largely true. The science wasn't there yet. But starting around 2004, a new field called event attribution emerged. The basic approach was to run climate models twice, once with human-caused greenhouse gases included, once without, and compare the probability of a given extreme event in each scenario. By the 2000s, these studies were being published within weeks of major events. The European heat wave of 2003, which killed tens of thousands, Hurricane Harvey's rainfall in 2017, the Australian bushfires of 2019 and 2020, the Pacific Northwest heat dome of 2021, which pushed temperatures in British Columbia to nearly 50 degrees Celsius, a temperature that would have been virtually impossible without climate change. Study after study showed the same pattern. Human-caused warming was making extreme events more likely, more intense, or both. And this brings us to something that had been lurking in the background of climate science for decades, but was now demanding center stage: the question of what to actually do about it. Because by the 2020s, the science was essentially settled in its broad outlines. The remaining uncertainties were about details and magnitudes, not about the fundamental direction. The question had shifted from, is this happening, to how fast, and what now? And the answers to those questions depended not just on physics and chemistry, but on technology, economics, politics, and something harder to quantify: collective human will. The engineering challenges alone were staggering. To decarbonize the global energy system, which in 2023 still derived roughly 80% of its primary energy from fossil fuels, within a few decades would require building out renewable energy, storage, transmission, and efficiency at a pace that had no historical precedent. And yet, some of the trends were genuinely encouraging. The cost of solar photovoltaic panels had fallen by more than 99% since the 1970s. Wind energy costs had dropped by roughly 70% over the previous decade, and onshore wind was now among the cheapest sources of electricity ever built in many parts of the world. Offshore wind was following the same trajectory, with enormous turbines, some with blades longer than a football field, being deployed in the North Sea, off the coast of the northeastern United States, and in the waters around East Asia. And here's the thing about these cost curves. They weren't slowing down. They were learning curves, driven by manufacturing scale, better materials, smarter designs, and the accumulated experience of building millions of units. Every time global solar capacity doubled, the cost per watt dropped by about 20 to 25%. That pattern had held for decades, and there was no obvious reason it had to stop. So by the early 2020s, the economics of clean electricity generation were, in many places, already favorable. Building a new solar or wind farm was cheaper than building a new coal or gas plant, and in some cases, cheaper than continuing to operate an existing one. That's a remarkable thing to be able to say, and it would have seemed wildly optimistic even 10 or 15 years earlier. But generating clean electricity is only part of the puzzle, and honestly, it might be the easier part. Because electricity accounts for only about 20 to 25% of total global energy use. The rest goes to transportation, industrial heat, building heating and cooling, agriculture, and chemical processes, sectors that are much harder to decarbonize. And this is where the engineering challenges get really interesting. Think about steel, for instance. The world produces roughly 1.9 billion tons of steel every year, and the conventional process, using blast furnaces fed with coking coal, is one of the largest industrial sources of carbon dioxide on Earth, responsible for something like 7 to 8% of global emissions. The coal isn't just fuel, it's a chemical reactant. Iron ore is iron oxide, and you need carbon to strip away the oxygen and leave you with metallic iron. That's basic chemistry, and it's been the foundation of steel making for centuries. So how do you make steel without carbon? One approach that was gaining real traction by the 2020s was to use hydrogen instead. Green hydrogen, made by splitting water with renewable electricity, can serve as the reducing agent, and instead of producing CO2, the byproduct is water. A Swedish consortium called Hybrit delivered the world's first fossil-free steel in 2021, and by 2023 and 2024, several companies were scaling up pilot plants. It works. The metallurgy is sound. But the challenge is scale and cost. You need enormous quantities of green hydrogen, which means enormous quantities of renewable electricity and electrolyzers, and you need it all to be cheap enough to compete with conventional steel that has had centuries of optimization. Cement is another giant. About 4.4 billion tons produced annually, roughly 8% of global CO2 emissions. And cement has the same kind of problem as steel. Part of the CO2 comes from burning fuel to heat the kiln to about 1,450 degrees Celsius, but more than half comes from the chemistry itself. When you heat limestone, calcium carbonate, to make clinker, you're literally driving off CO2 as a chemical reaction product. CaCO3 becomes CaO plus CO2. You can switch to clean fuel for the heat, but you still have that process emission to deal with. Carbon capture and storage becomes almost unavoidable for cement, or you need entirely new chemistries, geopolymers, novel binders, ways to mineralize CO2 back into building materials. People were working on all of these by the 2020s, and some were promising, but none had reached the scale needed to dent a 4 billion ton a year industry. Aviation, shipping, long-haul trucking. These are the sectors people in the energy world sometimes call hard to abate, and the name is accurate. You can electrify a car relatively easily because a car battery needs to store enough energy for a few hundred miles and can be recharged overnight. But a transatlantic flight requires energy densities that current batteries simply can't provide. Jet fuel packs, about 50 times more energy per kilogram than the best lithium-ion batteries. So for aviation, the leading options were sustainable aviation fuels, synthetic kerosene made from captured CO2, and green hydrogen, or biofuels from waste feedstocks, and potentially hydrogen for shorter routes. Each of these was technically feasible but expensive and far from scaled up. And then there's the question of energy storage, which is really the linchpin of the whole renewable energy transition. Because the sun doesn't always shine and the wind doesn't always blow. You've heard that 1,000 times. And it's true, and it matters. To run a grid primarily on variable renewables, you need storage. Lithium-ion batteries had followed their own spectacular cost curve, dropping about 97% in cost since their commercialization in the early 1990s. By 2023, battery packs for electric vehicles were approaching $100 per kilowatt hour, a threshold that many analysts considered the point at which EVs would reach upfront cost parity with internal combustion vehicles without subsidies. Grid-scale battery installations were growing exponentially. California alone had added gigawatts of battery storage in just a few years. But lithium-ion is great for hours of storage. What about days? Weeks? Seasonal storage? Storing summer solar energy for winter heating? That requires different technologies entirely. Pumped hydro, which has been around for over a century, is still the world's largest form of energy storage by far, but it needs specific geography. You need 2 reservoirs at different elevations. Compressed air, flow batteries, thermal storage, and yes, hydrogen again. All were being explored as long-duration storage solutions. The engineering is solvable. The question was whether it could be solved fast enough. And that word, fast, is really the crux of everything, because climate change isn't a problem you can solve eventually. It's a problem with a deadline, or more accurately, a budget. Remember the carbon budget concept, the total amount of CO2 humanity can emit while still having a reasonable chance of limiting warming to a given temperature? By the early 2020s, for a 50% chance of staying below 1.5 degrees of warming, the remaining budget was estimated at roughly 500 billion tons of CO2, and the world was emitting about 40 billion tons per year. You can do that arithmetic. It's not complicated, and it's not comforting. At current rates, that budget would be exhausted in about 12 to 13 years. Even for 2 degrees, the budget was larger, but still finite, maybe 1,150 billion tons, giving roughly 3 decades at current rates. So the engineering challenge wasn't just, can we build clean energy systems? It was, can we build them fast enough, at sufficient scale, while simultaneously transforming transportation, industry, agriculture, and land use across every country on Earth, in a time frame measured in decades rather than centuries? And that's a question that goes beyond engineering into economics, governance, justice, and human behavior, because the transition affects different people differently. Communities built around coal mining, oil-exporting nations whose entire economies depend on fossil fuel revenues, developing countries that have contributed least to historical emissions but face the greatest climate impacts and have the most urgent need for cheap energy to lift people out of poverty. The concept of climate justice, who bears the costs, who receives the benefits, who decides, was becoming central to every negotiation. But here's what I find genuinely remarkable, lying here thinking about this whole story from the beginning. Think about the arc of it. Fourier, sitting in his study in the 1820s, puzzling over why the Earth is warmer than bare physics would predict. Eunice Foote in 1856, filling glass jars with different gases and holding them in sunlight. Tyndall in his basement laboratory, finally proving which gases trap heat. Arrhenius spending a full year doing calculations by hand, to estimate what doubling CO2 would do to global temperature, and arriving at a number that, after more than a century of increasingly sophisticated science, has turned out to be remarkably close to our best modern estimates. Callendar, the amateur steam engineer, keeping meticulous records and being dismissed by the experts. Keeling, driving to the top of Mauna Loa to measure CO2 with an accuracy no one thought was necessary. Manabe, building the first real climate model on computers that had less processing power than a modern calculator. Hansen, walking into a Senate hearing room on the hottest day of the year and saying plainly what the science showed. Each of these people saw something. They noticed a pattern, asked a question, followed it stubbornly, often against skepticism or indifference, and added a piece to a picture that now, in the 2020s, is as clear as any major scientific finding in history. The greenhouse effect is real. Human activities are enhancing it. The Earth is warming. The consequences are already visible and will intensify. The physics hasn't changed since Tyndall's day. It's the same infrared absorption, the same radiative balance, the same water vapor feedbacks that Arrhenius sketched out in 1896. What's changed is the precision of our knowledge, the depth of our observations, and the urgency of the situation. And there's something almost poetic about the fact that this whole story, this entire scientific journey, comes back to something so simple. Certain molecules in the atmosphere vibrate at frequencies that match infrared radiation. That's it. That's the physical mechanism at the heart of everything. CO2 bends and stretches in ways that let it absorb and re-emit heat energy. Water vapor does the same. Methane, nitrous oxide, others. These molecular vibrations, invisible and silent, happening trillions upon trillions of times every second in the air above you right now. They are the reason Earth is habitable, and the reason that adding more of these molecules changes the climate. It's elegant in a way, simple at its core, staggeringly complex in its consequences, and the story isn't over. That's the honest truth. We're living in the middle of it. Maybe the most consequential chapter, the one where the choices get made that determine which version of the future actually arrives. The science has done its job. It identified the problem, quantified it, projected the outcomes, and pointed toward solutions. What happens next depends on decisions being made right now, in engineering labs and government ministries, in boardrooms and voting booths, in the way cities are planned and farms are managed and energy is generated and used. But tonight, you don't have to solve any of that. Tonight, it's enough to have followed this thread from the very beginning, from ancient Greek philosophers wondering about the nature of air, through centuries of patient observation and brilliant deduction, through wrong turns and corrections, through the slow accumulation of evidence that built one of the most thoroughly tested theories in all of science. It's a remarkable human achievement, this understanding. Thousands of people, across 2 centuries, speaking different languages, working in different fields, often unaware of each other's contributions, collectively assembling a picture of how our planet's atmosphere works and how we're changing it. So let that settle over you now like a blanket. The story of climate science is, at its heart, a story about paying attention, about noticing small things, a few parts per million here, a fraction of a degree there, and having the patience and the courage to follow where those observations lead. It's a story about human curiosity at its best, and whatever comes next, that curiosity isn't going anywhere. It's the same impulse that made Fourier wonder about the temperature of the Earth, that made Foote pick up those glass cylinders, that made Keeling drive up a volcano with his instruments. It's the impulse to understand, to measure, to know. And right now, that's a good thought to rest with. The air around you is doing exactly what Tyndall described, absorbing and re-emitting warmth, keeping the night from getting too cold, wrapping the planet in a thin, invisible layer of captured heat. It's been doing that for billions of years, and now you know why. So let your breathing slow, let your thoughts drift, and let the quiet hum of the atmosphere, those tiny molecular vibrations, too small to see, too important to ignore, carry you gently into sleep.